This video introduces force and stress in the context of rock mechanics. It should just be a review of the math that you've already learned in soil mechanics and from physics courses. To gauge your understanding of stress and force, please pause the video now and solve the following example. A stress of 10 MPa is applied to rock both vertically and horizontally. What is the stress normal to the plane at a 45-degree orientation? The answer is 10 MPa in this hydrostatic pressure question. If you answered 14 MPa or some other value than 10 MPa, do the math that you will be introduced to later in the video to convince yourself that 10 MPa is the right answer. You aren't alone if you answered this wrong. As engineering students, we are great at analytical solutions in the context of the classes we are taking. However, transferring the knowledge to the context of other applications may not always be obvious until somebody has walked us through it. The goal of this video is to do just that, to introduce you to stress and force using geology examples. This is a solution to that last problem on a Mohr circle, and I'll be talking about Mohr's circle later in the video. Consider a 3,500 kilogram rock with a base area of 1 meter by 1 meter sitting on the ground. In the photo, we have drilled a few cores out of that rock, so just pretend it's still a cube. What is the force applied to the ground by the rock, and what is the stress under the rock? The calculation of force is based on Newton's second law of motion, which is why the unit of force is the Newton. This 3,500 kilogram rock isn't moving, so it is only experiencing the downward force of gravity, which for rock mechanics we'll estimate at 10 meters per second squared. Estimation is common in the discipline of rock mechanics because measurement techniques for force and stress in rock is very challenging. So substituting, then we get that the force or weight under this 3,500 kilogram rock is 35 kilonewtons. So hint, on a test, if you're given the units of Newton, remember the apple and Newton himself to remember that you've been given a force. The mass of a substance or weight depends on what it is made of. That is, a 1 kilogram bar of gold weighs the same as a 1 kilogram bar of silver, even though the gold bar is about approximately half the size. If these 1 kilogram samples of silver and gold are on Earth, we can estimate the force on both of them to be 10 newtons. The only way to change the force is to go to another planet such as the Moon. There the force would be about 1.7 Newton. I want you to think in terms of units when I get to the Mohr circle, so that is why I'm showing you this concept here. Stress is just the force per unit area, or newtons per meter squared, which is 1 Pascal. And that unit is named after the famous French mathematician and physicist from the 16th century. So back to our rock with a 1 meter squared base, the stress underneath it is 35 kPa. In rock mechanics, we routinely test how much stress can be applied to a rock before it fails. We are really just adding mass as gravity is constant, and the area doesn't change during the test. We carefully prepare samples, usually rock core from diamond drilling, so the ends are parallel and flat, as this ensures full and complete contacts between the load and platings and the sample. In a UCS or unconfined compressive strength test, we load the sample by increasing the vertical force on it until it reaches the maximum load at which the sample fails. We'll assume that this particular sample failed at a stress of 100 MPa. We receive many different diameters of core, and testing has shown that UCS is dependent on specimen size. So that's why we always standardize and report on stress, which is the force per unit area. The 3,500 kilogram rock had a height of 1 meter. The depths of our mines, or drill holes for oil, are on the order of magnitude of several hundreds of meters to kilometers. So I stretched the photo I took of the 1 meter tall block, and now we can assume it is 1,000 meters tall. The stress under that size rock is 35 MPa. This calculation shows that at depths in mines or drill holes, expect stresses to be in the order of the MPa magnitude range. The actual value is going to depend on the density of the rock and the influences of geology. For instance, there are tectonic plates pushing against each other, faults, folding, and so on. All of those types of geological factors are going to influence the magnitude and direction of the forces in a rock at any given location, but stress will still always be in the order of magnitude of MPAs. So how do we know that there is stress? It could be signs like if we drill a hole and it was originally round, over time it might become oval, or we can see tunnels changing in shape. Because geological factors affect rock at depth, a rock mechanics engineer must be able to estimate stresses in different orientations. The UCS test specimen that was introduced earlier failed at an angle of approximately 60 degrees to the horizontal along a discontinuity. We can use the Mohr's circle to calculate what the shear stress was, I think of shearing as cutting, and normal stress were on the joint that broke during the test. The Mohr's circle is a useful tool in that it automatically incorporates the effects of force and area which change in relation to the orientation of the surface. The Mohr's circle places the principal stresses on the horizontal axis, while the vertical axis contains shear stress. Compressive stresses are positive for rock mechanics, so that is why the circle plots to the right of the origin. For any principal stress, the corresponding shear stress is 0. The minimum stress on our UCS sample plots as sigma 3, which was the left-hand coordinate on the x-axis of the circle, or 0 MPa. The maximum stress plots as sigma 1 on the right-hand coordinate of the axis at 100 MPa. Each point on the circle represents a different orientation of a plane, such as could be represented for the 60-degree plane of a rock, and provides the corresponding shear and normal stress components at that orientation. Remember that the unit of stress is pascals, or kilograms per meter per second squared. As stated earlier, gravity, which we'll assume is just taken into account in the second squared value here on the screen, that only changes if we change planets. So let's ignore the time component, as all of our calculations are on Earth, and think of the Mohr's stress circle only in terms of kilograms and meters. If you want a good visual for the effect of gravity, watch director Christopher Nolan's 2014 film Interstellar. So now this rock core from the UCS test is represented by its mass in kilograms on the right and a string of unit length in meter on the left. Now we can create the dimensionless Mohr's circle for this rock. I will take the string of unit length to represent the diameter of the circle for the 100 MPa rock core. Think of the rock and the string as a unit, in which the string is folded on top of the rock at an angle of 90 degrees, as shown on the right. Now to create the diameter of the circle, unfold the string, and the left intercept will be the confining stress, 0 MPa, which will be the left point of the circle, and the right intercept will be the stress at which the specimen failed, which is 100 MPa, and the right intercept on the circle. They are both plotted on the x-axis because the corresponding shear stresses are 0 for principal stresses. Once a circle is drawn with the diameter represented between the maximum and minimum principal stresses, all the points on this circle represent a stress at a different orientation for this given mass, this given unit length, and this given stress combination. In a few slides from now, I'm going to show how to calculate from first principles the stresses at different orientations, just so that we can prove that the Mohr's circle really works. Now we'll overlap the physical space of the specimen onto the Mohr diagram. I just took the 60-degree angle from the rock and put it on top of the Mohr's circle at the origin. When we learned the Mohr's circle, we were told to double the angles from physical space to put them onto the Mohr's diagram and measure counterclockwise. Our string from the physical space creates an angle of 120 degrees from the center of the Mohr's circle and shows why this rule works. This means that the shear and normal stresses are 25 and 43 MPa, which we will prove mathematically on the next couple of slides. When I drew this originally, I did it on scaled paper, and it's much easier to read off the correct values that way. With this exercise, I'm just trying to reinforce that the Mohr's circle is a representation of stress, which is a unit mass and a unit length. It is a great tool in that by knowing the minimum and maximum stresses on a specimen, one can quickly double the angle of the failure plane and measure off on the Mohr's circle to know what the corresponding shear and normal stresses are for that plane. Similarly, triaxial tests can be plotted the same way to a UCS test. With a triaxial test, a confining pressure is added to the side of the specimen, which is shown as 7 MPa here. And assuming that the specimen broke at 125 MPa, a plot of the corresponding circle is shown. Instead of using the Mohr circle, you can just memorize the stress equations for shear and normal stresses as shown here. These are derived in the appendix at the end of the presentation, and I encourage you to stop the video at that time and convince yourself that these equations really work. The key to using these equations is that you have to make sure the angle theta is in the configuration for the plane as determined from the derivation of the equation. From carefully drawing the Mohr circle and then confirming the calculation here, you should never get a problem wrong. The orientation of openings is one area in which a rock mechanics engineer may consider the direction of maximum stress. Think of a can full of pop. You could probably stand on top of it without damaging it. But if you try to stand on it sideways like on the right, it will guaranteed break. So if you could choose the orientation of a tunnel underground, and that tunnel is needed for a long time, it might be wise to line it up in the direction of the maximum stress and not minimum stress. So this is where I'm going to stop talking. The following slides show you the derivation of the mathematical equations for calculating stress. I encourage you to write these down and double check any solutions you do with the Mohr circle. I didn't use force calculations for almost 20 years and had to figure this out. There are so many great online resources to help you, like Khan Academy. I hope this video showed that the fundamentals you already know are really straightforward and can be applied to rock situations. I strongly suggest that you use algebra and Mohr circles as a way of always double checking your answers. Good luck.